So the plan for today is to continue working in chapter 2. So we've been working with second order differential equations with constant coefficients, homogeneous. And then today we're going to take a look at what happens now when we deal with the non-homogeneous case. So when we have some expression, non-zero expression on the right side of the equation. So that's the plan for today. We're going to be working with this worksheet 11. And then just so you know, we'll work on some stuff on Friday, on Wednesday, excuse me, maybe wrap that up next week. But the first exam is in 2 weeks, and that's going to cover chapters 1 and 2. So that'll cover first order, second order differential equations. So just keep in mind that. And otherwise, thank you for your responses on the early semester survey. I put this survey up last week. It's just to get some feedback from all of you. It's due tonight by midnight. And I said, if we get 80% response rate, I'll add a couple bonus points onto your exam. We're not there yet. So we have 17 or 18 responses last I checked out of 30-ish. So we're at about 50%. And so a lot of you might have been the ones that filled it out, but for anybody listening now or watching later, please do complete that survey. Okay, any questions before we get started? Okay, so then let's start by thinking about this problem on the worksheet 11. So let's consider this second order differential equation, x double prime second derivative of x plus 10x plus 9x equals 18. So we've talked about how we can find the homogeneous solution if we had this. Right, then we could set up the corresponding characteristic equation. And then get our homogeneous solution. So in this case, right, we find the roots of the characteristic equation, and then since they're two distinct real roots, we would plug them into our kind of general form for a homogeneous solution. Okay, but now we are adding this term over here. So clearly this is not going to work because I know if I plug that into the left side of the differential equation, we get 0. We don't get 18. So does anyone think of a solution? It doesn't need to be the most general solution, but what would a solution to that given differential equation be?
Could you just like add 18 to the C1e to the negative 9t plus C2?
You're saying like add a t in here?
No, just add 18 as a third number.
Yeah. Sorry, I think my volume was down low. So you mind repeating that again, Brian? Sorry.
Just like add 18 to it. So if you got 0. Yeah, just
okay. So you're saying if I add in 18 onto the end over here, that might do the trick.
Yeah.
And the thing you want to be careful about, so I know if I plug YH into that differential equation, I get 0. So if I were to plug this into the differential equation, right, the piece in red, that's going to give me 0. So let's just consider, I'm going to call this X with the subscript of P to denote a particular solution. And so maybe something like this could be a possibility. If I take the derivative of this, it's constant, so we would get 0, and we would get 0. And so plugging these values into the differential equation, would x equals 18 be a particular solution? let's test x equals 18. In other words, let's plug it into the differential equation over here and see if it works. So I would plug in the second derivative, that's 0. The first derivative of this is also 0 because we're proposing a constant solution. And then I would plug 18 in for x. This gives me 36, right, which is not equal to 18. So x equals 18 is not a solution. But maybe checking this helps figure out how we could fix that. So what can we do to fix it so that this would be a solution?
If x equals 2, if you added 2 instead of an 18.
Yeah, so let's try x equals 2 instead. So this one's not going to work, but if we try 2, the derivatives, since we have a constant function, all work out, and now we would have 0 plus 0 plus 2 times 2. That gives me 4, which is not equal to 18.
It's supposed to be 9.
Yes, okay. Let's try 9.
No, it's supposed to be 9x.
So if I try a 9x, then I actually don't know what x prime and x double prime are.
No. In the first equation, it's x double prime plus 10x prime plus 9x.
Yep.
Not 2x.
Where did I put a 2x? Oh, over here. Thank you.
On the last two, 18
Yeah.
and 2.
I got you.
Yeah.
Thanks. Yeah. Okay. And then the 2 works. Thank you. That does give us 18. Thank you. Sorry. And then that does check out. So x of p equals 2 does work. So plugging in this constant solution, x of p equals 2, would be a particular solution. It is not going to be the general solution, right? So today I want to focus on not finding general solutions, but finding a particular solution to the non-homogeneous part. And then finding the general solution is just going to be as simple as taking some information from the homogeneous solution and taking a particular solution and combining them together. But we'll focus on that part of the process on Wednesday. For today, I want to, again, just focus on how we can find solutions, particular solutions for the non-homogeneous part. And the one thing that I want to comment on here is that the way that we're going to do this is pretty similar to the way we did the the homogeneous part, which is we're going to kind of guess a form for what the solution would look like, and then we're going to try it and then figure out how we need to tweak it in order to get a particular solution. So kind of one thing to note here is that this non-homogeneous part over here, we'll just call this the forcing function. And we'll see why it gets called this when we revisit the mass spring problem. So in this case, forcing function is constant, and the particular solution which was 2, right? Our guess for the particular solution was the same type of function as the forcing function. So our forcing function was a constant, our guess was a constant. Any questions about this one so far? Mainly why x equals 18 was a reasonable guess, but didn't work, and then tweaking it to x equals 2 was a successful solution. Okay, so I'd like you to try and work on this one in some groups. So here we now have 18, we tweaked it, it's the same left side of the equation, but now we have 18 and there's a t over here. So using the same sort of process, which is come up with a guess, try your guess. If it doesn't work, refine your guess. See if discussing this with some of your classmates, you guys can figure out what a particular solution is. So again, you're not trying to give the most general solution. We're not trying to find the homogeneous solution. We're trying to find one specific function that would work as a solution. We'll call that a particular solution. Any questions about the task here? Okay, so I think it's good to try this guess and check because on your own without seeing exactly what you should guess, so that hopefully we will develop a game plan for how to attack some of these. Like if the forcing function is equal to this, this would be a reasonable guess for it. So that's how we're kind of working our way towards it. So I think it's helpful if why we're guessing certain things makes sense. So talking to a bunch of the groups seems like trying something like x is equal to 2t was or is a reasonable guess, kind of building off of the previous example that we did. But the problem with this one is now that the first derivative is not 0, right? So that complicates things a little bit more. Second derivative would be 0. And if you were to check this and plug everything into the differential equation up here, then we would get 0 plus 10 times 2 plus 9 times 2t should equal 18t. And so the 18t matches up, but you've got an additional 20 over here. So did one of the groups figure out how to, and kind of checking in with the groups I was able to, seemed like this was the point where a lot of people were at, and then coming up with some ideas about how to tweak this guess so that our original guess over here so that it would work out. Anybody want to share what their group did if you're happy with your result? Well, let's see. Okay, great. So a couple of groups are texting in the result. So if you want to send me a chat, not a text, a chat, just let me know, or just send it. I'll see it.
We could add a constant to x.
Yeah, so you can think about, well, we're off by a constant. That's right. So let's think about like adding some constant over here that would work it out. And you might think that, okay, we had an extra 20 over here. So maybe if we subtract that 20, that would balance out. The thing that you would want to be careful about is just remember that we're taking x, we're plugging it into the differential equation, and by multiplying it by 9. So we don't want to just subtract 20 here, but we need to also take into account we have this multiplication by 9. So if you're not sure what to do, if you're not sure how to fix this, then you can always check it. And find the value of b that will work. And this kind of takes us back to what we did in week 1, which was how do we check to see whether something is a solution to a differential equation. So here, our derivative is 2, second derivative is still 0, and this would give us x double prime is 0 plus 10 times 2 plus 9 times x. And now we have this additional undetermined constant b in our equation. So this gives us 20 plus 18t plus 9b should equal 18t. Sorry, I had a t over here. So the 18t's check out, but the we want the constant terms to cancel each other out. So now we can find the value of b that's going to perfectly cancel out that 20. And so if you kind of saw ahead that we want to get rid of that extra 20, and then we're going to multiply it by 9, so it makes sense to subtract 29ths, that's exactly the right thinking there. Good. And so a number of groups are texting this in. That's right. And so for now, you could ignore the homogeneous solution. So we're just trying to hone in on one particular solution that would work. And so what we just saw here is that one particular solution would be 2t minus 20 ninths. Any questions? So if we're trying to pick up on a pattern on our guesses, on the first one, we had a forcing function, which was constant. So we guessed that a constant function might be a good solution. And let's figure out which one would be. In question 2, we had a linear thing over here. And so our guess that we have over here, okay, maybe we wouldn't even know what the slope is just the most general linear function that we could think of. And then we'll figure out what the slope and the intercept need to be so that that is indeed a solution. And so if I have a cubic over here, I'm not going to solve this one, but at least what do you think would be a reasonable guess for a particular solution that might work?
It's either going to be a quadratic or a cubic function.
Okay, which do you think has a better chance of working?
I'd probably say quadratic, the one less than the highest order.
What do other people think? So we have a suggestion for a quadratic.
Cubic for sure.
What did you say, Brian? Sorry.
Cubic, because linear, you had a linear particular solution, so cubic would have cubic particular solution.
Yeah, so just kind of building off of this process of if my function is linear, I guess something linear. If my function is constant, I guess a constant function. So if the forcing function is cubic, then we're going to guess the most general cubic function that there is. And then we're going to take this and plug it into the differential equation, and we would get a corresponding system of 4 linear equations and 4 unknowns that we would have to solve for A, B, C, and D. Not going to do that here. Definitely not going to ask you to solve one that has like more than 3 undetermined coefficients on an exam for sure when you have some time. But that's the idea. So just so you know, for the reading quiz for next time, it's not going to be anything new. I just want to make sure that everybody takes a moment to digest what we're doing today. So it's going to be questions like, here's a differential equation. What would your guess for the particular solution be? So that's what I'm going to have you think about before Wednesday's class. But any questions? So the big takeaway here is that how are we going to find these particular solutions? We're going to come up with a reasonable guess, plug our guess in, and then solve for those undetermined coefficients. So it kind of goes step 1, come up with a reasonable guess, plug it in.
Can we assume that A equals 2 because that's going to be the only one with the highest enough exponent in t cubed to match 18t cubed?
Yep, that's true. Yeah, so if you want to use that, then that might cut down on one of your undetermineds. Yeah. Yeah, and that's the last step would be to solve for the undetermined coefficients. And this process is called the method of undetermined coefficients. Okay, and again, this is really the new part of this process. We know how to plug things into differential equations and check to see if there's solutions. So that part is kind of a reboot, but yeah, step one is come up with reasonable guess. So let's think about what might be reasonable guesses for these. So let's consider now forcing function which is given by a sign. And hopefully it makes sense that trying x of p equals to a polynomial is not reasonable. And kind of the gist here is when you take derivatives of polynomials, you get polynomials back. And so if my right side is not a polynomial, then I shouldn't be plugging a polynomial into the left side. So it makes sense that a trig function might work. Right, since taking derivative of sine gives me cosines and sines back. So if I have a sine of 2t on the right side, it makes sense that I might try and plug sine of 2t in on the left side. And for that same reason, this might be a reasonable guess too. So kind of the direction we're building in here is that our guess for the particular solution is going to should look similar to what the forcing function is. And here, if we try a guess, as our guess for the particular solution, then we can calculate the derivative using the chain rule. We get 2a cosine of 2t, and then the second derivative would give me minus for a sine of 2t. And if I try plugging this back into the differential equation over here, we're going to have problems getting this to work out. And why is that?
That pesky cosine.
Yeah, we've got this cosine from the first derivative. So certainly we could probably balance out the difference of, the second derivative and x, because x is a sine, second derivative is a sine, but there's not going to be a way that we could get rid of the first derivative term, which has a cosine. And we would have the same problem if we tried b cosine of t. The cosines might cancel out, and what might be left over could be a sine, right? So it's possible that this one could work out because we actually want a sine on this side of the equation. But there is some dependency in that when I take the derivative of a cosine, I get a sine and vice versa. So when we're dealing with trig functions, we can see that this, in this case, can't work for ours since we'll have a cosine term this one doesn't work either in this case. So what might be a good general guess that has a better chance of working?
Mam said she's getting chili ranos.
Sorry, Brian?
Oh, never mind. I didn't know my mic was on. Sorry.
Oh.
Chili rellenos?
So A, cosine sine t doesn't work. B, cosine 2t doesn't work. So should I stop guessing trig functions and try something else? Nobody has a thought on what we might be able to do? Let's see. Sorry, there's a chat. So there was a guess for tangent. And again, what you want to think about is what might happen if I plug that in. And if I plug in tangent, I'll get secant squared, and then I take the derivative of that. It's going to get a little bit complicated. So I do want to guess trig functions. And now people are sending in some good guesses, which is, why don't we take a combination of sines and cosines? So the more terms we include in our guess, right, the more flexibility we're going to have in correcting things, but we don't want to add unnecessary things in because that's just going to make the algebra unnecessarily difficult. So we're trying to kind of come up with this balance of guessing something general enough, but not just, including every possible function under the sun. So in this case, trying something like, let's take both the sine and the cosine and see if some combination of both of these is going to give us the right balance. So let's actually work this one out just so that we can see what these look like. And I won't have room over here. So I'm just going to add a blank page below. And so here, what was the differential equation? X double prime, was it plus 10x prime plus 9x was 85 sine 2t. So how this method of undetermined coefficients works, again, is step one is you come up with a guess. And again, your guess, generally speaking, is gonna be that my particular solution has the same form as the forcing function. Okay, and that's what I mean by the forcing function. So if our forcing function is trig with a 2 inside, let me use same letters, then we can guess A, sine of 2t plus B, cosine of 2t. Sorry, we've got a delay in my writing. Let me try this.
Just so we know kind of where we're headed, are we going towards Euler's formula for combination of sine and cosine?
We're not going to have to worry about Euler's formula here. That's going to only come into play when we're possibly dealing with the homogeneous, when we're trying to find the homogeneous solution and we get complex imaginary roots. For the guess, we're not going to have to worry about guessing imaginary things. So we're only going to guess real valued functions. So if we want to see if this works out, right, then we're going to take the first derivative, which would give me 2a cosine of 2t. And then we're going to take the derivative of the other term, which has a sign change now. So we would get minus 2b times the sine of 2t. And hopefully it makes sense why this is a good guess, because now when we add and subtract first, second derivatives, we get the possibility of the sines and the cosines all canceling out just so. And now we would get a negative 4a times the sine of 2t, and we would have a minus 4b times the cosine of 2t. So far, we're just doing take the derivative and plug it into the differential equation. So the differential equation says we are going to take 1 times the second derivative plus 10 times the first derivative plus 9 times the original function. Any questions while I'm writing away? So there's our x double prime term, and then we've got plus 10 times x prime. So I'll just multiply that out. That would give me 20a cosine of 2t minus 20b. Sine of 2t. So all of this stuff comes from the 9 times the first derivative. This was the second derivative. And then lastly, we need to add to that 9 times x, which would give me 9a times the sine of 2t plus 9b times the cosine of 2t. And this piece comes from the 9x times b. And then what we need is the left side. If this is going to be a solution, I think we had sine, should give me 85 times the sine of 2t. So this is kind of step 2, which is plug it in and check.
Just on that one that you did right there in blue, like when you were trying to, match them up, shouldn't that be, it's correct like how it's written out in red, but shouldn't it be 10 xp prime instead of 9?
Yeah, thank you. That's right. That's
okay, cool.
Yep. Okay, and then kind of the last step is to solve for a and b. So what might be a good plan of attack for that?
Grouping sines and cosines together and creating 2 equations, and then taking the sine 2t and cosine 2t out and solving a system of equations.
Yep, let's kind of group all of these sine terms, right, and all of the cosine terms together, and then we'll have one equation, which is we need a and b to give me the right coefficient in front of the sine, and we need an a and a b to give me the right coefficient in front of the cosine. And let me just say, we actually have like a 0 times a cosine of 2t over here. So we want to make sure the cosines cancel out and the sines give me 85 So let's group them together. So for the sines, we have minus 4a, we have a minus 20b, we have a plus 9a, all of that should give me the correct sine expression from the forcing function. So that's one equation. And then we have a second equation from the cosine terms, which would be minus 4b, we have minus, a plus 20a and a plus 9b. And they should all cancel out so that none of the cosines remain. So from this, we get one equation, which is 5a minus 20b. That should equal 85. That comes from this equation, setting all of this stuff equal to 85. And we have the same from the other equation, which would be 20a plus 5b is equal to 0. And from this, solving that system, I think what you should wind up with is a is equal to 1 and b is equal to minus 4. And I think that would work out. But here you can solve this system of linear equations in any number of ways. And again, you should verify that a is 1, b is minus 4. So that gives us a particular solution of the a was what we call the coefficient in front of the sine. Sorry, my iPad froze for a sec. All right, so we found a is 1. So again, that was the coefficient in front of the sine, and b is minus 4. That was the coefficient in front of the cosine. So let me just say we've found one solution, but not the general solution at this point. And we'll talk about this more next time, but if you're worrying, well, what good does this do me if I want to find the general solution? The way that you would generate a general solution would be to take the homogeneous solution, the general homogeneous solution, and then just add on this particular solution. Any questions?
So for the first portion, the homogeneous section, do we just completely ignore the 85 sine 2t and just solve the left?
Yep.
Okay.
That's right. And the reason why is, this expression over here, whatever it is, when you plug it into the left side, it gives you 0. So it's not going to add any confusion as far as matching up the particular solution.
Okay. Thank you.
Yep. But we can prove that next time a little more carefully.
We've done polynomials and trig. What about like exponents or other nasty things?
Yeah, so good. But so any question about this one? And then we can kind of summarize what we've got so far. And again, this will be important because this is the type of stuff that you guys are going to have to do on the reading quiz. So if the forcing function, we'll call it f of t, is equal to, let me just put it like this. If our forcing function is a polynomial of degree n, right, then we would guess the most general looking polynomial of that same degree. And that's what we saw in the first couple of questions. When we had constant, we guessed constant. When we had linear, we guessed linear. When we had cubic, we guessed cubic. And then let me also say that if we have a trig function whether it's sine or cosine, maybe let me, rather than use b here, use a beta t, then we guess both of the trig and the cosine functions with the same period, so with the same value of b. Our guess here would be a times the sine of beta t plus b times the cosine of beta t. So that's what we can see from the first couple of examples. And let me add one more to this. And so one last one that we'll consider is if our forcing function is equal to e to the kt, maybe we have some constant times it. So maybe we have ax double prime plus bx prime plus cx is equal to e to the kt. If we have something like this over here, then what do you think a reasonable guess would be for the particular solution? Anybody have any thoughts?
E to the kt.
Yeah, and we'll just put undetermined coefficient there. We're going to guess the same looking exponential. And so again, the idea here is just use your intuition. Whatever the forcing function looks like, we're going to guess something that looks just like it. And you just want to be careful in the case for the trig that in this case, you need to include both the sine and the cosine to keep things as general as possible. Okay, any questions? Okay, so let's now consider differential equation that looks like this in question number 5. So now we've changed the left side of the differential equation. So we've got second derivative of x plus 25x equals 10 cosine 5t. So building off of what we just discussed, excuse me, this would be a reasonable guess. This being this combination of sine and cosine, right, that have the same beta value of the given one. This one is not going to work here. Does anyone see why this one would cause problems or is gonna not work no matter what we try for A and B? How would you solve this, going back to what we talked about the last couple of classes?
You would use the characteristic equation.
Yeah, so we would use the characteristic equation, which would be r squared plus 25 is equal to 0. So this has imaginary roots, plus or minus 5i, which means the homogeneous solution, I'll just denote that with an h, would look like C1 sine of 5t plus C2 cosine of 5t, right? Since the a to the alpha t part is alpha is 0 here, that part would be just be 1. And so the guess here is actually a general solution to the homogeneous differential equation. So that means if I were to take this guess and test it and plug it into this differential equation, since it's a homogeneous solution, on the left side, we're definitely going to get 0. And on the right side, we would have 10 times the cosine of 5t. So there's no way that that would work out. This is why this is doomed to fail. So when our initial guess is a homogeneous solution, okay, then we have what is called resonance. Okay, and this is what causes bridges to collapse and wine glasses to shatter, is exactly this occurrence of resonance. If our forcing function has the same period as our homogeneous solution, then weird things can happen. And so rather than guess, just to kind of look ahead a little bit, when we have resonance, then we need to tweak our initial guess. So we had an initial guess over here, which looked like the given forcing function, but we noticed that this is actually just the homogeneous solution. So we're going to take our initial guess and just multiply it by a power of t, similar to what we did when we had repeated roots for the homogeneous case. So let me just modify our table over here. Okay, so then we multiply our first guess by a power of t. So that applies to these scenarios in our table. So in this case, we do have resonance. So rather than just guess a sine beta t plus b cosine of beta t, we add this t in our guess over here. So if you've got a guess that looks like this, then you would take the derivative of that and plug it into the differential, or first and second derivatives of this, plug it into the differential equation and solve for a and b. And just be careful that when you do this, just be sure you apply the product and chain rules carefully, as well as with x double prime. So the calculus here becomes a little bit more complicated just because our function has this extra t, but otherwise same process. So I'll just leave this as an exercise. Which is to find these coefficients a and b so that x of p is indeed a solution. I don't want to go through that; it's pretty tedious, but I'll just write up the solutions and you can check it later. Any questions so far?
So the only difference between this one and the last one we just did, it didn't have the first derivative.
So the difference between this one and the previous ones is not necessarily that the first derivative is missing. It's just that the forcing function that we had over here, based on it, our guess would be exactly the same as the homogeneous solution. So the idea is when you're coming up with your guess, you want to consider what is the homogeneous solution and then see if you have resonance with the forcing function. So I've got some examples that are going to just highlight this idea of how can we identify when we have resonance versus when we don't have resonance. That's a tricky thing maybe to pick up on. But the reason why we had to tweak this one was not so much that it was missing the first derivative, just that the homogeneous solution looks similar to the forcing function. So that adds some complexity. Okay, so yeah, so this is what I want to think about before we go today. And so we can think about the first couple of ones together. And so what I've done here is for each of these is I've found the homogeneous solution just using the process we were working on last week. But let me just say, this is not something that would be given to you, right? So if we're trying to do this method of undetermined coefficients, there's kind of a step 0 now. Which is really what you need to do first. And you're going to need that to find the general solution anyway. Since your answer to that might mean that you have some resonance, and then you might need to multiply your guess by a power of t. So if I'm trying to work on question 6 and figure out whether or not I'm going to have to adjust my initial guess, this is the one that we just did together. And so for this one, you would find the homogeneous solution and you get this. And then you can see that this has the same sort of form as the homogeneous solution. So you again, might initially guess that a good reasonable thing would be to guess a trig function that looks similar to the forcing function. But again, this is the homogeneous solution exactly, right? All we've done is just rewritten the homogeneous solution. So we know that one is not going to work. So this one does have resonance, we would say. And question 7 is saying, well, if you have resonance, what would your guess be? And remember, what we do is we take our original guess and just multiply it by the power of t. And that one would work for certain values of a and b. And then if we kind of compare this to what is going on in B, but sorry, let me just pause. Any questions on the first one? Okay, and so in B, we have the same left side, so we have the same homogeneous solution. In this one, if I'm looking at a forcing function of 10 times e to the 5t, what do you think would be a good particular solution to guess initially here? So what did we say would be good guesses if a forcing function is exponential?
The e to the 5t.
Yeah, we would guess something similar. Yes, and thanks for the chats coming in. We would guess something similar as the forcing function. So we would guess the most general looking exponential that has a power of 5t. And then I compare this guess with the homogeneous solution. And for this one, we would not have any resonance, right? Because these look totally different. Homogeneous solution has trig stuff in it with the same period. And our guess for a particular solution is exponential. So there's no resonance between those at all. One is exponential, one is trig. But even moreover, what we're really saying is that this particular solution doesn't resemble the homogeneous solution at all. So we don't have any resonance here. So our guess, if we're just kind of keeping track of this in B, since this one doesn't have any resonance, we don't need to add that extra power of t. Okay, any questions? So I will leave you to think about these. And then we can compare. I'm not going to send this into breakout rooms just because we've got just 5 minutes left. But I'd like you to at least think about some of these. And if you don't get through all of them, that's fine. And the idea here is to just get comfortable with identifying when things have resonance and when they don't, and then coming up with a guess. And if you have any questions, feel free to just chat me privately. I'll see them in the chat. so let's just check in on how you are doing with these. So I'm just going to open up a poll to see what you guys thought about part C. So did you think that C had resonance or not? Okay, thanks for the responses. If you haven't gotten it in, take another second, please, to get it in. Okay, so here were the responses. So let's see, it looks like 14 people said to some extent no resonance, and 2 said there is some resonance and we had a not sure. So for this one does not have resonance. So for those that said no resonance, that is true. And the reason why is if this is my forcing function, then my initial guess here, just to keep track of these, would be x of p is equal to AE, and here the power was 5t again. And then you look at, oh, sorry, I was doing B. C was this one over here, excuse me. So our guess would not be an exponential, sorry. It would be some combination of cosine 5t and sine of 5t. And so comparing this, to the homogeneous solution, they're totally different. So that's why we're not going to have any resonance with that one. And so just to wrap this one up, this one does have resonance, this one does have resonance, and this one does not have resonance. So you can kind of check your thinking if you were able to get through all of them, but we're out of time today.
Okay, for F, sorry to interrupt. So if there's an e to the negative t in front of the cosines and the homogeneous solution, that does not mean there's resonance because that e to the negative t is not there.
That's right. So to think about F, so let me just say, we'll pick up from this next time, and I do want to just respect that we're out of time, or at least you're free to go. I'll stick around if you have some questions. Feel free to stick around. So to answer Abraham's question about in 6F, why is there not resonance? The guess here, right, would be this, which is not exactly the same as that one exactly because of this stuff here. So it needs to look almost exactly the same, just off by a constant. And so, yes, so this one would not have any resonance because if I plug this into the differential equation, the left side, we won't get 0. So there's not going to be a problem with that.
Okay, cool.
Yeah. Whereas if you looked at E, in E, you do have the E part and the trig part that match up. So that's why there's resonance there.
And then for E, the particular solution would be A times e to the negative t sine 4t plus B times, you would just add an e to the negative t in each term, right?
Yeah, so in E, you initially would guess like A, e to the minus t cosine, what was it, 4t. plus b e to the minus t sine of 4t. And then when you write out this as my guess, and you compare it to the homogeneous solution that's over here, you can see that they look exactly the same. We just called one A and B, and the other one C1 and C2. So that's why there is resonance. And so you do need to then multiply this by t to fix it.
Cool.
Yeah, so down here, you would have an extra power of t.
Thank you.
Yep, no problem.